So, talking about a function of three variables. I want to step up the integral. What does it mean to do a triple integral? Well, then my function must be a function of three variables. So if I have a function of three variables, what the hell is that? We've had this discussion before. A function of three variables represents something like temperature at a point in space, the magnetic field, the electric field at different places in three dimensions. You can talk about what's the temperature, what things change as I go in different directions. So that means that the domain I'm working on is now a region in R3. Let me do the same thing I did with double integral. The easiest region to work on in double integral was a rectangle. So the easiest region to work on in three dimensions is a box. Oh, okay, wait a minute. This is going to be in the X direction, the Y direction, the Z direction, respectively. And then I'll do the same thing I did with the rectangle. I divided the rectangle up into little boxes and called them dA. I'm going to divide this up into little bitty cubes, and I'll call them dV. Now, they don't actually have to be cubes. They could be rectangles. They don't have to be the same length, width, and height, but it's easier in my head to picture them as a bunch of little cubes stacked together. And on page 1029 is a very nice picture that shows exactly this idea. From A to B in the X's, from C to D in the Y's, from E to F in the Z's, I get these little bitty cubes, and they're dx by dy by dz. There. Now you can actually see the picture. So I think about this little thing. And I say to myself, in the rectangles, remember our snowfall approximations, our temperature approximations, you pick a point somewhere in the middle of the square, call that the value, and then multiply by dV. I'm going to do the same thing here. Pick some point in the midst of this, call it f of xyz star, multiply that by the volume, and then I'll add them all up. And that gives me this triple Riemann sum right here. But I'm going from 1 to n with respect to x, 1 to m with respect to y, 1 to L with respect to Z. I'm losing track of my indices here. I just have to go all three ways to fit everything together, right? Add up all of the boxes in whatever order you want. And then we'll do a triple integral. Just like with our temperature discussion or our snowfall discussion, we're getting an approximate value here. And I say the same thing. The way to make an approximation more exact is to do more rectangles. So I let the number of rectangles go off to infinity. Well, that turns a sum into an integral. The triple integral over the box B, that was the name of our box, of f of xyz dv. So I have defined our integral in exactly the same way we defined the double integral, in exactly the same way we defined the single integral, by looking at the limit of an approximation. Questions on the definition? The best possible thing to work on is a box. Because when my function is continuous, Fubini's theorem still applies. And that turns a triple integral, just like a double integral, into an iterated integral. And I can do them dx, dy, dz, dz, dy, dx, dy, dz, dx, in any order I want. I could do dx, dy, dz. I could do dx, dz, dy. I could do dy, dx, dz, dy, dz, dx. I could do dz, dx, dy, dz, dy, dx. Doesn't matter which of the six I pick, but these differentials need to match the order of the limits of integration from inside to outside. So A and B goes with dx, C and D goes with dy, E and F goes with dz. Permute the order of the differentials, permute the order of the limits in exactly the same way. An example. I want you to do the triple integral over the box given by -1 to 1 in x, 0 to 2 in y, 0 to 1 in z. I want you to do the integral of x squared, I'm sorry, xz minus y cubed dv. What order are we going to do these in? What's your order for the differentials? Pick one. We're going to do at least two, so pick one.
Like the longer they're listed at, like -1, 1.
So we'll do dx, dy, dz?
Yeah.
Okay. So if I'm going to do that, then this integral becomes xz minus y cubed dx, dy, dz. That means the -1 and the 1 are on the inside. The 0 and the 2 are on the middle. and the 0 and the 1 are on the outside. I've put them in the order that matches the differential choice. But that means I'm integrating with respect to x first. What is the integral of xz with respect to x? Z is a constant as far as x is concerned. What about y cubed? Right, we get an x. So I've done my integral in x. Now I got to plug in and subtract. One half times 1 squared is 1/2. So I get 1/2 z minus 1y cubed minus, put in -1. 1/2 times -1 squared is 1/2. Minus -1 makes that a plus y cubed. What happens? Okay. 2y cubed, integrate with respect to y, and you get from 0 to 2. I really should write y equals there because I have another option for a letter. Plug in 2 and you get -4. -4. -8. Because it's half of 16. Plug in 0, you get 0. So this is the integral from 0 to 1 of -8 dz. That's -8z from 0 to 1, and I get -8. If I were to be a real pain in the ass, I would say there are 5 of you. There are 5 other orders. Each of you do a different one. I'm not going to do it. Let's pick another one though, because I claim that it doesn't matter what order we do these in. It should work the same in any way. So we did dx, dy, dz. I want another order. So y being first means 0 and 2 go on the inside. Z being second means 0 and 1 go on the second. And x being last means -1 and 1 go on the outside. Because that matches y, z, x. Okay, I'm integrating with respect to y first. What's the antiderivative in terms of y? Plug in 2, plug in 0. Plug in 2, I get 2xz minus 4. Plug in 0, I get 0. 0xz minus 1/4 of 0 to the 4th. dz, dx. But now I iterate my next integral. So I integrate with respect to z. What's my integral with respect to z?
That's square.
Plug in 1, plug in 0. And you get the integral from -1 to 1 of x minus 4, 1, 1, x minus 4, and then plug in 0, you get 0 dx. From -1 to 1, we get 1/2 x squared minus 4x. Put in 1 and you get 1/2 minus 4. Put in -1 and you get 1/2 minus -4. And that gives me a -8. When my function is continuous, they're all going to be the same. It doesn't matter which order we do it in when it's a box. Questions? This is what I mean by Calc 3 is just Calc 1 with more. We did the same integrals we've already done. We just treated the other letters like they were numbers. By the way, I did do dx, dy, dz in my notes. But then in my notes, I did dz, dy, dx. It's still -8. But I could do any of the 6 possible orders. I should get -8 for every one of them. What if it's not a box? We typically change from B to E. I don't know why, but E is a region in 3 dimensions. Here is where the article in our Canvas page, triple integrals for the sketching impaired, may or may not be useful to you. It's your call. I'm a very visual person, so I'm going to draw a bunch of pictures. And even if they're absolute crap drawings, I'm going to try to explain what I'm making an attempt at so we can figure out how to do these integrals. But what I want to think about is where are my boundaries easiest to look at? Are they easiest to look at as a top and a bottom? Z is a function of xy as a top. Z is a function of xy on the bottom. We'll call that a type 1 region. On the other hand, we could do a type 2 region or a type 3 region. A type 2 region would have a front and a back. X equals as a front, X equals as a back. Type 3 region has a left and a right. Y equals a function of X and Z. Y equals a function of X and Z. I don't care what type they are. I just think about it as a top, a bottom, a front, a back, or a left and a right as my first boundary. So I could say, I've got a bottom and a top. I'll do an example of this in a moment. But if I have a bottom and a top, then those two pieces have to live over a region in the XY plane. Which means I'd want to do dz first. Because if I integrate dz, then I'll replace z's with x's and y's. Here is a description of a 3D region. Now, I'm going to draw a picture. But let me think about this before I draw it. My first gut reaction is that there are a lot of different options for me to figure out what this looks like. But I'm going to start with those two. Because that's just X and Y. There's no Z in there at all. That's a region in the XY plane. So let's figure out what the region in the XY plane looks like. What's that pair of equations? Describe for me in X and Y. If I'm doing this in X and Y, it's either type 1 or type 2. How is that written? As type 1 or type 2? Or should I think of that dy dx or dx dy? I want to think of it as type 2. The numbers are on y, the functions are on x, so I'm going to do x first and then y. I'd have to rearrange this equation, or do you mean type 1 and 3D?
You rearrange the equation. So you get y equals square root of 4 minus x squared. And then
Why? Walk me through getting there.
you make x equals 4 square root of 4 minus y squared, and then you solve for y.
Okay. And I could rearrange that, right? But instead of rearranging, let me just ask, what's that curve? What is this the equation of? A circle whose center is the origin and whose radius is 2. And I'm going from 0 to the positive square root and y is only going from 0 to 2. So my region in the xy plane is actually a quarter circle. Now here's the 3D part. This equation lives above that circle. So I'm about to make a really crappy 3D picture. There's my quarter circle. Right? Now, let's think of a top and a bottom living over this quarter circle. Look at the equation Z. Z equals 0. What does the equation Z equals 0 represent? Actually, no. The equation Z equals 0 on its own. Not worrying about this part. Z equals 0 is a plane. It's the XY plane. It's where this curve lives, but it's the XY plane. So that's the equation Z equals 0. What about the equation Z equals Y? What's that represent? That's the line in the YZ plane with a slope of 1, right? Which really makes it a plane at an angle of 45 degrees to the XY. So above this, that's in the ZY plane. I've drawn that right here flat on the board. But I need to follow this curve as well. That curve is going to start up here in this corner. And it's going to ride along the upper plane, which means as we get closer to the x-axis, it's got to come down. So in front, there's like a curved wall that comes down to that point. I've taken a cylinder. I've cut a quarter of a cylinder, and then I've sliced it at an angle. I have a roof and a floor, right? The roof is the surface, Z equals Y. The floor is the surface, Z equals 0. So I can now think of the triple integral I'll make up a function, zy dv. Oh, sorry, zx, not zy. I got to look at my notes properly. Integral zx dv can now be thought of as the integral from 0 to y dz, and then over r dA. You'll notice I didn't write it dx dy dz or dz dx dy or any like that, right? I just said, oh, I'm going to do this one first, and then I'll have a double integral. What do you think the best way is to do that double integral over that region R? That would work. I could do a type 1. I could do a type 2. But it's part of a circle. I'm probably best switching to polar when I do. So see, I'm going to try and bring all of that together. Hey, look, this is really a triple integral, but it's really a z integral and then an xy integral. And because this one's round, I'm better off doing polar coordinates. So let me do it like this first. I'm integrating with respect to z. What's the integral with respect to z? But z equals 0, z equals y, so you get 1/2 y squared x minus 0. And now I'm back to what we were doing last week. This is a polar. In polar, this is much easier than it is as a type 1 or a type 2. Now, that's not to say I can't do it as a type 1 or a type 2, but I think it's a whole crap ton easier to do this in polar. If I switch to polar, what's R, my region in the XY plane? Roll back up. There's my region. Which makes this a polar rectangle. It's bounded by numbers. So now all I have to do is switch all of this to polar coordinates. And then dA is RD theta. I'm ready to rock and roll. 1/2, the 1/2 is just going to stay there. Y squared. Y squared. What's Y in polar? So I'll get an R squared sine squared theta. Then cosine x. X gives me a cosine, so I get an R cosine theta, and then RD theta. Notice that this is a bunch of stuff with thetas multiplied by a bunch of stuff in R's. My favorite thing happens here. What's my favorite thing to do with double integrals like this? The corollary to Fubini's theorem. My favorite thing to do with a double integral like this. It's something in R times something in theta. I can rip them apart and do an R integral and a theta integral. 1, 2, 3, 4 R's. So I get the integral from 0 to 2, or 1/2 outside, R to the 4th dr, and then the integral from 0 to pi over 2 sine squared theta cosine theta d theta. Because they're all multiplied. There's no adding, there's no subtracting. I can just spread the multiplications apart. That's my corollary to Fubini. He's my favorite guy for this position. How do I do the second integral here? First one, power rule. How do I do the second one? U equals, and so du is cosine of theta. Makes my life a lot easier, doesn't it? I get u squared. U squared du, the antiderivative of u squared is u cubed over 3. I plug it back into theta.
We'll show that.
We've done these substitutions so often, we can do them on that side spectrum. Yeah. Okay, now I just have to plug in. I get 1/10. 2 to the 5th is 32 minus 0. Sine of pi over 2 is 1 cubed. 1 cubed is 1. Sine of 0 is 0. So I get 32 over 3. The hardest part of this problem. The worst part of this, figuring out the balanced point integral. The integrals themselves, power rule and a trig use of. Piece of cake. Hard, set it up. Questions?
You really gone from the board to the second.
It is up to me to decide. Do I want to think of this as top and bottom, front and back, or left and right? But once I've decided top and bottom, then I look and I say, oh, there's a region in the XY plane where this volume lives. So I'm going to treat that region in the XY plane as a region R, and I'll figure out how to do the double integral over that. Remember our Easter egg, the ellipsoids? We said there was a top and a bottom. And Nora even said, hey, isn't that a triple? Well, it's a top and a bottom. And I said, oh, but they live over this circle. That's the same calculation. It's up to us to decide how we want to do this. Here we go. Here's just a description of a region. I want you to draw this region because you've seen this sucker before. It's way back in chapter 12. Now, a tetrahedron means it's made of 4 triangles. It's got 4 corners. The corners are the origin, the point 1 unit out the x-axis, 2 units out the y-axis, and 3 units up the z-axis. So the edges, given that I'm a crap artist, we'll just kind of make them believe straight lines, right? Here's our thing. Wait a minute. That's the description of a plane in 3D, right? I've got 3 points. They make up a plane. But you can think of this plane as a top living over some region in X and Y. You could think of it as a front living over some region in Y and Z. You could think of it as a right side living over some region in X and Z. I don't even want to set up an integral. I just want to try and write the different ways to bound this. To do that, I need to know the equation of this plane. Oh, crap. How do we do the equation for something again? This was on exam 1.
Well, this is zero, is equal to the gradient of x.
But to do the gradient, I need a function, right? I have a function here. How am I going to figure that out? I know for a fact that this equation for a plane should look like this, right? And it's got to go through those 3 points. 1, 2, 3. Yes? But those are also the intercepts, aren't they? If I put in 1, 0, 0, then I get A equals D. If I put in 0, 2, 0, I get 2B equals D. If I put in 0, 0, 3, I get 3C equals D. Give me a number that's divisible by 1 and by 2 and by 3. So let's use D equals 6 and write out the equation. And now I have the equation for the plane is 6x plus 3y plus 2z equals 6. Ta-da! I could try and figure out some functional gradient to go here. I know that my change in x is -3, and I know my change in y is -3 over 2. So I could write z minus z0 equals minus fx times x minus x0, and so on, right? I could do that because I have the slopes at that point, 0, 0, 3. And those slopes are constant because this is the plane. I like this. It's a lot faster. Especially when I have the intercepts. So now, I got a question for you. If we do this as top and bottom, or front and back, or right and left, we have to rewrite this equation appropriately. I'm going to do all 3. But let's figure out which one you want to do first. So, which one do you want to do first? Do it as front and back in X, do it as right and left in Y, or do it as top and bottom in Z? Okay, if I'm doing it as left and right, then I'm thinking of Y as the direction we are going first. That means this equation needs to be written Y equals. Now, let me think about this just geometrically for a moment. This piece of this plane, this triangular shape, is in the first octant. X and Y and Z are all positive. What is our left edge?
X is 0.
X is?
And Z.
X and Z are, X and Z are not both 0 because that would be a straight line. I'm looking at this wall, right? The right-hand wall. That's where y is equal to 0. That's the x is z plane, isn't it? That's this side over here. That's y equals 0. The right-hand side is the surface of our equation, but I got to rewrite the equation to be y equals. Okay, wait a minute. That means taking this and rearranging it. So I've got 3y equals 6 minus 6x minus 2z. I divide by 3. I get y equals 2 minus 2x minus 2/3 z. So my boundary in y looks like that. With me so far? I go back to this picture. The xz plane where y equals 0 has a triangle in it. Let's draw that triangle. Wait a minute. I know the triangle has one corner at 0, one corner at 1 when x is equal to 1, and a corner when x is equal to 3. This is our region. And now you have a choice. Do you want to do this dx dz or dz dx? We're going to do both. Pick which one we're starting with. Okay, so if I start dx dz, then x has to be in equations, which means I need the equation for this line as x equals. But given the way I drew it, I'm not sure I know the equation x equals. Given the way I drew it, wouldn't it make more sense to do this z equals? Z is the up and down. So let's actually start by doing this as z equals. What's the equation for that line in terms of v? It's a line. What's its slope? What's its intercept? Which means if I rewrite that as x equals, 3x equals negative z plus 3, or x equals negative 1/3 z plus 3. Over 3, wait a minute, that's a 1. Got to write it down right, man. So that would be the upper x, right? I'm going x first. So that would be this x, negative 1/3 z plus 1. And the left x would be 0. And then z goes from where to where? Now notice, look at the 3 equations we've got. Here our equation in y has 2 variables in it. Here our equation in x only has 1 variable in it. Here our equations have no variables in it. 2, 1, 0. Made my life easier as I went down, didn't it? On the other hand, I could write z going from 0 to negative 3x plus 3, and x going from 0 to 1. That would be the other version of that same triangle, wouldn't it? Now, I will tell you, you picked doing y first. But I could just as easily do x first. If I did x first, then I would leave the triangle from this picture in the YZ plane. And if I did z first, I need the triangle in the XY plane. I need to go down and take away the variable I was just dealing with. Again, here is where that paper that's on our Canvas page about triple integrals for the sketching impaired is helpful. By the way, the integral of 1 dv. The integral over e of 1 dv is the volume of E. Just like the integral of 1 gives us an area, the integral of 1 gives us a volume when I'm dealing with triple integrals. If you have a density function, then you can do mass, moments of inertia, center of mass, probability density. All of the applications we did last week work in triples as well. And they're more meaningful to physics. Mass, center of mass, moments of inertia in 3D are more accurate and more meaningful than they are in 2D because we live in a 3D world. You want to do more? We can do quadruple integrals, quintuple integrals. I don't care how many integrals you want, as long as it's continuous. Rubinian applies. I just have to do it. I can't draw any more pictures. They don't look. I don't hallucinate well enough to see 5-dimensional integrals. Wednesday's question and answer day. Because we had the video last week, and then we had the application on surface area, and now triple integrals. 3 sections, let's have a Q&A. I'll see you all then. Have a wonderful rest of your day.